good morning, or good afternoon, everyone, depending on where you are joining us from, and welcome to today's webinar. My name is Kalina from Business Review, and I will be your host today. It is our pleasure to have Promecon Process Measurement Control GmbH with us today, who will be presenting this webinar titled Fuel Mass Flow Measurement for Coal and Biomass-Fired Boilers. Today's guest speaker is Hans-Georg Konrad, CEO, President of Promecon. I would like to welcome you to our webinar platform on 24. You will notice that this webinar is browser-based, so if you disconnect for any reason, please just click on the link that you received via email to rejoin the session. In order to ask any questions, you can send them in via the questions widget at the top corner of your screen and click Submit. Towards the end of the session, we will allocate some time to address any questions or thoughts that you may have. Please use the yellow Help widget if you require any assistance. And you can also move, resize, and maximize any of the windows in front of you to get a better view of the slides. But now, please allow me to welcome Hans-Georg Konrad. Hans, over to you.
Well, thank you very much for this kind introduction, and welcome to everybody who is joining in today. I'm very happy that I have heard a lot of people have signed up for this. We have a lot of listeners, hundreds, I must say, around the world, from all parts, so from east to west, all with similar issues, similar problems about combustion. And I'll be very happy to talk about combustion today. For those who have not seen Promecon yet, or who don't know us as of yet, let me just tell you a few words about our company. We are based here in Germany, not far away from the city of Berlin, in a small town called Magdeburg, and our premises are located in the small village of Barleben. And from here we serve a lot of countries and a lot of clients in the thermal process industry to optimize their process. So we are talking about energy production, we're talking about cement production, steel making, and other industries that have high energy throughput and need to optimize their process. Maybe to start with, give you a little bit of an impression where we are doing projects basically all around the world. And I have selected three industries that we are quite active in, which is power stations, steel plants, as well as cement plants. And you can see that basically in every part of the world, we have so far optimized process. And again, we are quite experienced in a range of thermal processes. But today I would like to talk again about power generation, because it's one of the biggest industries, and especially coal-fired and increasingly biomass-fired power generation is the backbone of the electricity production in the world. So I think it is a very important issue, and it will remain a very important issue over the next decades to keep those power stations as environmental friendly and as efficient as possible. So before I go into today's session, I would like to just have a broad overview over the products that we are installing and commissioning for power stations. These are airflow measurements. Of course, there's a lot of airflow in your boilers, primary airflow, secondary airflow, but also gas flow that goes to the precipitators and out the stack. I've had an extensive session on this before, and I have talked about the difficulties of accurate airflow measurement in the power station, which I find one of the most neglected issues in power generation, because in many areas people don't know what the accurate airflow is into the boiler, and that is an essential part of making the boiler better. On top of that, we have an unburned carbon monitor for better fly ash measurement. And that means for better fly ash management, so in terms of fly ash disposal, but also in terms of better efficiency and better combustion control. And then today, of course, I will focus on the main topic, which is the measurement of fuel flow into your boiler. Yeah? Fuel flow for us means, in this case, solid fuel, which is transported into the boiler by a pneumatic transport. So it can be coal flow, it can be biomass, any pulverized fuel. Now, and you can see that in this picture here, the pulverized coal measurement on the mill. And I will dive into this issue today to show you how important it is to have a correct coal flow measurement and an optimized coal flow distribution. And I will touch upon all the aspects that are important to improve your combustion. Now, the other measurements I talked about, the air flows, flue gas flows, the unburned carbon, as well as the measurement in the stack. So this is the complete range of what we do, but today we would like to focus on the coal flow. Coal flow is measured in traditional power stations by the feeder that goes to the pulverizer, right? So each pulverizer will have a certain coal feed in, and then it will respond with a certain outflow from the pulverizer classifier into the burners. Now, what is happening after the coal has entered into the burners? The coal will start to combust. And the most important curve that one who is dealing with combustion has to know, of course, is the combustion constituents. So you can see this curve, which tells you how much O2, how much NOx, and how much loss on ignition and CO you get for the combustion. We use this curve very often to explain why the measurement of unburned carbon is so important in order to tune your combustion correctly. Before you can do that, however, you must be able to have the same coal mass flow going to each burner, because every burner has this curve. Every burner has an optimum zone of combustion where you have a right fit of excess air versus fuel. And this optimum zone is the only zone where your combustion can be maximized for efficiency and also maximized for NOx reduction. So if you have 6 burners in a row, you have 6 of these curves. Very important. If you have 20 burners, you have 20 of these curves. Yeah? Many people take these curves only for a total boiler. So the boiler, if I lower my O2, I see at some point my CO is going up, which you can see on the left-hand side of the picture. But the reality is, it's not only the CO in the whole boiler going up, it can be the CO of 1 or 2 or 3 burners spiking first. And as you can see, the CO is an exponential function. So a few burners can spoil your day. So this is why I have talked about the right airflow measurement on a burner by burner level the last time that I had this conference webinar. And today, of course, I'm talking about the other part, the other half. What's the other half? The other half is the fuel. So having the right combustion air is one thing, having the right combustion fuel amount to each burner is the other thing. So that's the second big important part in order to optimize your combustion. Fuel flow measurement, how do we do that? Every mill has certain outputs. Some mills have 4 outlets if you have a tangentially fired boiler, for example. If you have a wall-fired boiler, then of course you can have a different number. You can have 5 outlets or 6. But the fact is, one mill serves several burners. So if you make the change to the feeder, all burners change. But each burner has a different flow. And it's not only true that each burner has a different flow as compared to another burner in average, but also each burner has a fluctuating flow. So the fuel flow over time is not consistent. It's going up and down all the time. And that's also something that no one really can say. How much is that fluctuation? If you can only get to know this if you measure properly. So let's start with the first part of this presentation with coal flow measurement. How do we measure coal flow? Traditionally, coal flow is measured by extractive methods. So you have an isokinetic sampler or a rotor probe or some sort of device where you suck coal dust out of a pipe. There are several severe issues with this. The first one is you do not have an instantaneous result for all 4 pipes. It takes you 15 minutes to do a single measurement. And usually this is done on a pipe-by-pipe basis. So it takes you about 1 hour to measure 1 round of pipes in a mill. Now, you will see a couple of pictures later on in this presentation where you can see what happens in a few minutes in a mill. These can be very massive and severe changes. You can have very abrupt changes over time. So what if the mill is not steady whilst you're doing that? You will have no clear picture of what's happening. The second problem is that you have a huge tendency of the coal mass flow to form a rope in the pipe. So you don't have the same amount of fuel in a certain area in the pipe, but you will have a huge amount of fuel on one corner or another. So if you do this manual measurement, you will have to do a great deal of care. You have to take great care in order to level out the distribution. Now, what is different in our measurement? We have a measurement that measures the coal density and the coal velocity separately. The coal density means how much coal dust is present in one section length of pipe. So let's assume you have 2-3 meters of pipe. In this case, we insert 2 sensors on the top of the pipe. The 2 sensors are a transmitting sensor and a receiving sensor for the microwaves. What are these sensors doing? These sensors, the transmitter, sends a microwave along the pipe. So it's really a long wavelength, a low frequency microwave going along the pipe, being reflected on the outer reflector rods and going back. So the wave is going back and forth and forms a resonance. So we emit a microwave that forms a resonance at a certain resonance frequency. The receiving antenna receives that resonance. Now, as you add more coal dust or more biomass dust into the pipe, this resonance frequency will slightly shift downwards to a lower frequency. And that shift is proportional to the amount of solid concentration in the pipe. So if you have twice the concentration in one pipe than in the other, the frequency shift will be twice as big. As simple as that. With this density measurement, you can detect very important features, and I will talk about why it's so important and what we are detecting. But the basic thing is we can detect how much solid material is present in a certain length of pipe. 2 meters of pipe, how many grams of solid material are present right now in this split second? 80 grams, 90 grams? That's what we measure with density. Now, when you measure density, you don't know the coal mass flow. The coal mass flow is something different. To know the coal mass flow, you have to take the density and you have to multiply it with the velocity. You have to multiply coal concentration, how many grams per meter of pipe, times meter per second in order to arrive at grams per second mass flow. How do we measure velocity? As I mentioned, we have 2 antennas in the pipe to do the microwave measurement. These 2 antennas are also used for a completely different measurement. And this measurement is called cross-correlation measurement. Each antenna can sense electric current. Now, as the particles go by the antenna, they are all electrically charged. This is because of the pneumatic transport of the particles. And the charged particles forming a charged cloud will induce an opposite charge on the antenna. So if you have a positive cloud of particles going by the antenna, you will have a negative charge on the antenna for a short period of time. And when the cloud moves away, it will become neutral again. So you have what we call a fingerprint or a time signature of all the particles that go by the antenna. Now we have 2 antennae. So we have the first one and the second one. Their distance is about 300 millimeters. So if you now have a pattern of flow that you can see on antenna number 1 and you can see it on antenna number 2, you will find this flow is very similar. but the flow is time shifted. Let me show you that in an example. You can see here the particles going by the antennas. Now, when you look closely to the signal, you can see the signal that we are generating are very similar. You can see that with your own eyes. You have the particles going by, you have the two time signatures. If you now put these two time signatures on top of each other, you can see, yes, they are matching, but they are time shifted, right? This is the time shift. So what do we do now? We take these two signals and we put them into a cross-correlation filter. And what a cross-correlation filter does, it takes two signals and it starts to match the two signals on top of each other, and it checks out at which time shift do these signals have the best match. This is called cross-correlation function. Now in this example, of course, you will see the cross-correlation function gives you a time. So we measure a time shift, and since the sensors have a distance, we have time and distance. So distance over time gives us velocity. So we have two independent measurements, one for density, one for velocity. And this is very important when you want to optimize your mill. So after explaining how the system works, I would like to dive a little bit more into why we need these measurement properties in order to optimize your combustion. First, let's have a quick look at how the system is specified. We measure absolute coal mass flow to each coal pipe. Now, most of the people I talk to say this is clear, because you have to know how many kilograms of coal go into the burner, and then I have so many kilograms of air going into the burner, and that match must be the right stoichiometry. That's correct. So that is one thing. The other thing, however, is we also need to measure the velocity. Why is the velocity important? The velocity is important, of course, because each burner is designed for a certain velocity. And let me tell you, in many plants you have vastly different velocities. One burner very fast, blowing the flame very far into the boiler, difficulties with flame attachment. And another burner, the flame very slow, the flame burning back onto the burner nozzle, damaging the burner. We have seen so many damaged burners in our life, and it's usually just because of wrong velocities. So velocity is a big point. Now, this all needs to be measured within a certain accuracy, that's clear. Now, here comes another thing that's very intimately tied to velocity, and this is the detection of deposit in the pipe. Now, many people say, why should I measure deposit? You have to measure deposit because as soon as you get that, your coal pipe will start storing in the coal. So the coal that comes out of the classifier is not really going to the burner anymore, but it is stored inside the pipe, and it will come out later in some random way. How you will see that? You will see, of course, that your flame starts pulsating. You will have a very uneven flame. And you will, of course, have high NOx formation, high CO formation, all the rest of it. So detecting the coal deposit is important. What do you do if you detect the coal deposit? You increase your primary air. Sometimes only a little increase, 5%, is enough. If you have variable orifices in your ducts, you can detune your variable orifice slightly, and you will see one pipe blows free, all the pipes are great. So knowing the deposit of your coal pipe is very important. And then, of course, the system is installed quickly and easy. Why is it important? Because sometimes you need to also see the critical point in your pipe far away. So sometimes you install a sensor on a vertical section of your coal pipe, and you install the sensor later on a long, far away horizontal spot in order to determine, is the coal still traveling nicely at that spot, right? So the coal comes out of the mill very nicely, and the further it travels and the closer it gets to the burner, the more pulsating the flow becomes. Flow and transport conditions are key to good combustion, and that is at least as important as the levelness of your coal flow. That's something that people very rarely have in mind. You have to also look at the consistency of your flow. So here you can see a system, a main panel. You can see a local control box. So we have a main panel. We have a local control box where you can hook up to 4 sensors or 4 channels, 4 pipes. And then you can hook up so many local boxes to a control panel. Then you can see the sensors, the reflector rods, the cables. So nothing really exciting. The application is more exciting than the sensors. There's not much to see. Basically, the technology works very well. Here you can see typical installation points. That is now a wall-fired unit, single wall. You have 4 mills. You have some horizontal sections where the sensors have been installed and some vertical sections. It really depends on how the pipe runs are. But there's always an issue, or there's always a discussion between our people whether we should install our sensors on a vertical section close to the classifier, or whether we should them install close to the burner. And the burner tuning people always like the installation close to the burner, because they say, I have to be aware of what's going into the burner. I don't care of what comes out of the mill. And there is a difference, especially in the dynamics of the flow, which we will see later in some further comments. Here you can see a typical installation example. Yeah? So it's a drill and tap installation. You drill a few holes into the pipe. You can tap them with a small plug. And later on, you can insert the sensors and the reflector rods. You don't need to make big modifications to the pipe in order to install our system, even on an existing mill. Here you can see another installation example. So the sensors are going in here in a horizontal pipe. Very simple and easy installation. So we have to talk about another very important issue. When you are measuring coal flow distribution and you find that you have a problem, how do you correct the problem? That is at least as big an issue as the measurement itself. We have many clients, they see they have a problem, what can they do about it? And there have been many attempts in the power industry to fix it. Most of them with variable orifices. So you have an orifice in the pipe that changes the diameter of the pipe, and by this you change the flow resistance from the classifier to the burner. Good idea, but this only helps you with velocity distribution. Yeah? A variable orifice will help you with velocity equalization. It will not help you necessarily with mass flow. Why is that? Here you can see in a small schematic the outlet or the turret of a mill. You can see the outlet pipe, and you can see this big basket-like case below where the coal or the PF is swirling upwards, and as it swirls upwards it hits one pipe and then it goes out the pipe. Now you must understand that many ropes that you have are already originating from the mill. So you have a rope that is spiraling up the turret and it hits one pipe. So this one rope hits one pipe. Two things. First of all, this big rope is now missing in all the other pipes. So very often the concentration difference between the pipes is massive. It's much bigger than the velocity difference. The second thing is once that the rope is in the pipe, it will never turn around. You can't make it go back. You have a rise velocity in your turret of 1 meter per second or 1.5 meters. And once it's in the pipe, it's 20 meters per second. It's gone, right? So you have to deflect that rope before it enters your coal pipe or your PF pipe. And you can see that here we have these little pedal dampers. As the rope goes up, in this case, if you turn the dampers down, the rope is deflected. And what does the rope do? The rope will go on to the next pipe and hit the next pipe and then go up in the next pipe. So you have a way of keeping high concentration out of individual pipes. What do you do if your pipe has too little PF? You can turn the blades the other way to catch more PF in. We have found that the mill outlet is the most effective point of pushing coal from one pipe to the other. That's by far the most effective point, and you do not influence the coal velocity much with this. So here you can have a drawing. You see how this looks like. You have all these pedals there installed below the outlets. Yeah. If you want to see this in live pictures, here are the live, it's an example of an installation that we have done. You have the pedals as an assembly, and then you can see how the pedals are mounted on the mill. You can see here the mill turret, the outlet, where the pedals have been installed. So you modify the outlet, put the pedals in. And here you can see, finally, this is where the pedals have been installed on the mill turret, on the outlet, and can be moved easily. Not a big deal to do. What can you do with this? If this is your outlet before you have installed the pedals, then this is your outlet after you have regulated the coal mass flow. This is by far the best way to move coal from one pipe to the other and have the same coal flow on every pipe. Or to show you another example, this is a typical example of a coal distribution project that we have done. 6 pipes from one mill before and after. Right? Now, what is the effect of the flow balancing? The effect of the flow balancing, of course, is that you gain a lot of O2 headroom. Right? If your flows are balanced now, the airflow is balanced, as I showed in my last lecture, and now the fuel flow is balanced, your whole boiler can live with quite a lot less excess air. Right? So to put that in here, on the left-hand side, you can see with an unbalanced boiler, you run some pipes under stoichiometric and some over stoichiometric. If you balance the pipes, and they're all stoichiometric, you can pull back the excess air a lot. And that means you have less boiler loss. You have a huge reduction in FD and ID fan power. So optimizing the efficiency of your boiler or the excess air ratio of your boiler is a big help in maximizing efficiency. And of course, needless to say, you also reduce the formation of CO, you also reduce the unburned carbon, and you reduce NOx. So all thermal problems that you have and all stoichiometric problems that you have can be reduced. Here are some typical examples of efficiency and NOx reduction, efficiency increase in NOx reduction. You can see the NOx has been going down, and in this case, the use of NH3 has been reducing as well. The NOx went down by 24%. The NH3 consumption went down by 28%. Now you might ask yourself, why has the NH3 consumption dropped more than the primary NOx? Why? Because by the better distribution, we have also reduced ammonia slip. So also the effectiveness of the NH3 was increased by leveling out the temperatures across the furnace and have a better combustion with a lower ammonia slip. Now here's another problem I've already touched upon, and that is pulsation of flow. Many boilers suffer from the fact that the burners are not giving a consistent flame, but the flame is pushing, pulsating in and out. That means your flame is never running in the right stoichiometry. Yeah? You have this low NOx burner, this wonderful thing, very, very expensive, and you see that it's never running in the right stoichiometry. Why? In many cases, long pipes are storing in the coal. So you have coal on the bottom of the pipe, and that's pushed out only occasionally. You can see actually that the coal level is building up. We can sometimes see that also in the velocities that are rising. And at a certain point, the coal then is pushed as a dune or a plug further along, and sometime it reaches the burner, and then it just bulges into the flame, uncontrolled, gives huge CO spikes, and gives you a bad combustion. Yeah. Many clients I visit in Asia, but also in Europe, actually everywhere, have this problem. Very often I see power stations where the paint has come off the coal pipe. Said, look, you had a fire in your coal pipe. Yeah, it happens from time to time. This is all a sign of coal deposit and uncontrolled coal transport. And when you have biomass, this problem gets far worse. We have biomass clients that are struggling with the biomass transport. No, I must say we have no biomass client that is not struggling with this. I must say from when we started in Scandinavia years ago with biomass measurement, there always has been a problem with the biomass getting to the burner in a consistent way without blocking. And this problem is mainly caused by a pulsation in coal or biomass density and by inappropriate transport velocities. So if you have a look at some live data, this is a typical example of this. We have 4 pipes. On the upper diagram, you can see the mass flow. Or basically, you can actually see the density or the concentration of the material. Yeah? So you can see there is density. Now, if you look at this, actually all pipes are looking quite nice, except for the pink one. The pink pipe seems to spike up in an erratic way from time to time. What does it mean? It means that you have a thin layer. And when I say a thin layer, I mean a few millimeters, 5, 6, 7 millimeters of solid material lying on the ground of the pipe. And this thin layer is not moving because it's deposit, but it's changing in thickness up and down, and this change is exactly the noise that you see in the picture. So, frankly speaking, the density measurement here is correct. The flow measurement that we are now forming out of velocity and density, of course, is not correct because part of the material is not moving, it's just lying on the ground. But the point is that even a flow measurement would not help you much because you don't know when this flow is going to arrive at your burner. The material will just flow for another 2-3 meters and then it will settle again and again and again. You don't know when it's going to arrive at your burner. So what have we done? On the lower picture, you can see velocities. So what we have asked the client to do is to increase his primary air velocity slightly. Say, look, crank the primary air velocity up just to see what happens. And needless to say, what happened? The primary air rise brought the fact that velocity dropped down and the whole measurement was very consistent, perfect flow. And after that, we asked the client to drop the velocity again, and there was a problem again. So what can you do with this? You can use this device in order to determine the minimum necessary transport velocity in every pipe that you have. And this is very important. Because in many combustion systems, you would like to know what is the minimum amount of PA that I need in order to get the coal to the burner. High PA flows have adverse effect on a lot of things. For example, on particle size, on flame length, flame attachment. But they're also having a bad effect on the combustion. Yeah? The primary air is the first air that sees the flame. And the primary air, it has a big impact on NOx formation. So you would like to tune the primary air in order to have the perfect flame, but you also need to know what is the primary air, the minimum primary air that I need in order to get the coal to the flame in the first place. And that is what nobody knows. Today, nobody can tell, are my coal pipes clean? Will the coal really go from the mill to the burner or not? With our system, you can see that. You have an online detection mechanism to tell you this pipe is too slow, this pipe is fine. And now please go back. Many of you, especially if you are located in Asia, you have, in your modern power stations, you have variable orifices. So now you can say, I would like to raise that pipe slightly and lower this pipe so that all the pipes are basically good for coal transport, and that's my minimum velocity that I need in order to get the coal to the burner. Very important feature in order to get a stable flame. Remember, if you have a difference in coal flow and you level out, you equalize the difference in coal flow, that's fine. But if all your coal transport properties, if your mass flow is pulsating, you don't gain much because your flames will stay over and under stoichiometric at the same time because there is no steady input of fuel. Fuel pulsation is one of the worst problems. So with that technology, you can mitigate that. Here another example. Very often what we see on the left-hand side, you can see the graph. Again, the pink curve, you can see the pink curve going all the way up to the roof. This is the density that we measure. And that means that obviously there is a huge deposit in the pipe. And later on, when we increase the air at the end of that graph, as you see the lower graph, that's the transport velocities, you can see that the density all of a sudden collapses again. So this was a typical example of a pipe filling up with material and then being released again. Very common problem. Now, I don't want to say what can happen if you don't take care of that. I was talking about the paint that comes off the pipes sometimes because you have the pipes overheating and there's a fire. This is what can happen if you have inadequate velocities. But even if it doesn't get as catastrophic as that, the right velocities are key in order to get your combustion right. Now, everything I've told you for now means that you can make changes to the coal mass flow distribution from one burner to the other, and you can try to stabilize your flow between the classifier and the burner. So leveling coal flow from burner to burner and leveling coal flow over time, so you have a consistent flow. This is, I would say, 90%, 95% of what you can do to make your combustion really better. I've seen a lot of hardware solutions, a lot of repiping, revamping of burners, of mill outlets. I tell you, the most important thing is that you can measure what you're doing and that you have something to adjust. You need to have an adjustment. So your variable orifices are fine for velocity, and the pedal dampers that I showed you are essential in order to be able to move the coal from one pipe to the other before it enters the pipe. Coal mass flow control is done before the coal enters the pipe, not inside the pipe. That's too late. Yeah. Okay, this is basically what I wanted to talk about today. I have another very important issue, which is, of course, the control of the plant itself. I know that many of you have issues with NOx, with unburned carbon. You would like to make your combustion better. But for many of you, also in Asia, the renewable energy is on the horizon. Now, if I judge the energy situation correctly, I don't see renewable energy taking over the world power productions soon, because the amount of energy needed is just so vast that it cannot be replaced by renewables easily. The other thing is, I don't see storage technologies inside that are capable of bridging times where there's no renewable energy available. So what many coal-fired stations and many biomass-fired stations in the future will have to do is serve as load swing capacity units. So in Europe we have that quite a bit. You have units ramping up and down in power and equalizing the grid fluctuations that you have from renewable energy. Now you can guess what comes now. What is the bottleneck if you have a coal-fired power station? What is the bottleneck if you want to ramp up the boiler output? The bottleneck is, of course, the pulverizer. You have a pulverizer that has several minutes of delay time before the coal that goes in comes out. And this delay time is not a constant. It depends on roller pressure, hard growth index of the coal. It depends on your masses in the mill. Do you have a high level, a low level? There are many, many parameters. And in this case, the mill is more or less a black box that you don't know what the mill is doing. You don't know what is inside the mill. You can only measure what goes into the mill, and you can hope for the best when it comes out. Now, I want you to think about one thing. If the mill is running on a stable load, and you make a slow change, what happens? Not much, because even if you have a 3-minute delay, what you change here changes then with a certain delay at the output. But what happens if you make a rapid change? You have the input go up quickly, then suddenly the output comes later, yeah? But there is a huge gap, and that gap is unknown. You don't know how long it is. If you have a large load jump in a mill, 30 seconds can be endless. Do you know what can happen for 30 seconds if your feed water pump is not adjusted properly, if your airflow is not adjusted properly? How much boiler stress will you get if you have such a large transient and you don't know how to synchronize the firepower of your burners correctly because you don't know how much the mill is spitting out? Now, the solution to this, of course, is also cold flow measurement of Promecon. We have cold flow measurement on the outlet of a mill, and this cold flow measurement tells us how much the mill is putting out. Now, of course, if you say this is enough to make a better boiler control, that's not correct, because the output is very noisy. As you have seen, the mill is not putting out the coal in a very consistent way, but there are a lot of fluctuations and there's a lot of dynamics in the signals. So what you have to do is you have to monitor what's inside the mill. You have to monitor the masses in the mill. How much coal do you have in the mill? Now, I mentioned before, the mill is a black box, right? So how do you do this? Well, the answer here is that you have a state controller that takes the feeder as an input, the airflow as an input, the delta P as an input, the coal flow out as an output, and the airflow as an output. And by this, you are able to create a state space that watches the internal state variables inside the mill. So you can then calculate online the amount of masses in the mill. And that allows you to control the mill to see how much bed depth do I have and how much do I have to increase roller pressure in order to blow it all out in a certain amount of time. We have done this in a power station in Germany. That was one of the first power stations where we have performed this. We have a state controller that was monitoring the mill, but it was also monitoring the fuel controller, the feed water pump, the boiler pressure. And with this, we have been able to do load jumps in a much better way than we have done them before. So on the left-hand side, you can see an uncontrolled load jump with a lot of swing and a lot of problems and a lot of boiler stress. And on the right-hand side, you can see a much smoother transition using the latest technology from Promecon, including the state controller. And the way this works, of course, is that you have a feeder, you have the mill, and you can see the mill is the biggest time delay, the biggest time constant in this whole line. And this time constant is unknown. And by introducing the Promecon measurement, the controller now knows when this element in the control chain will start reacting. And by this, it is far easier to optimize the boiler response and have the boiler reacting better. Now, one other thing I would like to mention here, and this is quite interesting, we are just beginning to dive into this, and we will have a far more data available in the next month on this issue, because it's a very, very interesting subject. And this is mill dynamics on the burners. If you have a constant feeder into your mill and you have a constant airflow into your mill, what we have seen with the installations that we are currently doing is that you have a very big fluctuation on the outlet of your mill. Your mill is not completely constant in the outlet because the mill has pulsations. So the coal level inside the mill fluctuates. The coal output fluctuates. So you have a constant feeder in, but the mill is doing this all the time. So the mill already gives you a large fluctuation that will show up on the burners later on. This is especially a problem with low-grade fuels and also with biomass. So the idea is here to use the state controller in order to vary the inputs to the mill, so let the feeder dynamically go up and down in order to keep the inner state variables of the mill constant. Yeah? So we try to optimize the mill so that the bed depth is constant. And the result is that the output gets far more constant. Yeah? So in this picture you can see, once we vary the feeder accordingly, the output gets more constant. It's a little bit like balancing a broomstick. You have an input variable that you keep on going back and forth with in order to keep the output constant. And an example of that is this one here, where we have a mill. You can see that red line that's with the controller switched off on the left-hand side, and on the right-hand side the controller is switched on. And you can see how the output of the mill stabilizes vastly after we have switched on the controller. Yeah. And I can only tell you, in summer we will have another webinar in June, end of June, where I will talk more about this property of how to control your fuel input to the boiler with this state controller. It could help a lot of power stations to get rid of the feeder bias, but also have a far more consistent fuel feed to the boiler from the mills. Because many mills are pulsating on their outlet, and people can't measure it. People don't realize it. So that brings me to the end of this session. I hope that you have seen some interesting news from us and some interesting aspects of how to optimize your combustion system. And I'm now happy to take your questions and answer any of the questions that you might have. Thank you very much.
Thank you very much, Hans, for this wonderful presentation. Indeed, it is now time for our Q&A session. Just a reminder for the audience members that in order to ask questions, you can send them in via the questions widget at the top corner of your screen. We'll try to cover as many questions as we can in today's session, but your questions will also be available to be answered at a later date. It looks like we've got quite a few questions coming through already. So the first one for today is, what is the calibration mechanism for the density and velocity sensors? I wonder that system will give useful results in the start, but as we move on, the calibration difference between sensors will increase and we won't get the same wavefronts from both sensors. Do you have any experience of long-term, 5 years plus performance of this system at any power plant?
Mm-hmm. Yes, very, very straightforward, very important question. First of all, can I click onto this? Okay. Yes, first of all, we have our experience is about 25 years, and this is the first system that we brought to the market. Now, what is this system doing? This system is measuring time. And it's measuring time for the frequency shift as well as for the velocity. And I will explain how this is done. You have a frequency shift in the pipe. Yeah, you have the pipe, you have the two sensors, and you measure the resonance frequency. A frequency measurement is a time measurement. It's measured by a quartz oscillator. Now, digital time measurement devices, of course, they have a drift, but the drift is 10 to the minus 6, 10 to the minus 7. Time measurement is the most accurate long-term measurement that mankind ever invented. And modern quartz-stabilized time clocks are extremely accurate. You could actually say practically they don't drift over their lifetime. So therefore, if you have this frequency measurement, the frequency measurement will always be based on the same time measurement. So the drift is 0. What can change? Well, what can change is that the pipe will over time have a slightly different 0 offset, yeah? Because over time the wall thickness will change, or there will be some material sticking to the pipe. In this case, the 0 point could slowly go away and go take a different position. Now, how do you account for that? When you blow the mill empty, when you take the mill out, you will see the empty pipes. And the system will recognize what the frequency was at the last empty cycle. So if there's a difference, you will get an alarm telling you your system is not zeroed accurately, so you have to, it's basically a tear, like you have on a weigh scale. So you have to tear the system from time to time for frequency. For velocity, I must say, velocity has no drift at all, and also no mechanism for re-zeroing, because there is no zero. We measure a direct time shift. The systems that we have put in years ago, 10 years ago, they have never been recalibrated. No plant has ever changed any calibration in order to readjust them. Those systems are calibrated for life.
Thank you very much. Another question that we have is, hi Hans, you showed us multiple pipe exit from mills and paddles to divert rope or break rope. What about single pipe outlets? So a different paddle arrangement before bifurcator or trifurcator will be required. Am I right?
Yes, that is, the answer is already contained in the question, absolutely correct. If you have bifurcators or trifurcators, you will then have a baffle plate, or basically a diverter plate that you can move left to right. And that works equally well. The only thing that you would have to make sure is that if you have a rope in the pipe that is going very fast, you have to make sure that the bifurcator plate, the diverter, is working halfway okay. Because if you have a rope that's hanging in one corner, you can have a very non-linear relationship between diverter plate position and split. So it might be a bit fiddly to get it stabilized, but the picture I've shown you with the 6 pipes that we have gotten together, that was with exactly such an arrangement. 3 outlets on the mill top, and then bifurcators on each pipe, so you have a common outlet of 3 pipes, and then 6 pipes at the end. So that basically it works very well.
Thank you very much. The next question is corrosion an issue?
Erosion is certainly an issue in coal pipes, but you have to be very clear about which places. Our sensors and our reflector rods are in the full velocity profile of this. So these are made out of very hard tungsten carbide materials that don't wear. If I say they don't wear, I would say they last for 10, 15 years, right? So we have long-term experience with very low abrasion on these parts, and of course we use the appropriate materials. When you talk about the pedals that go in the classifier before the outlet, you have to keep in mind that the velocities at that location are completely different from the ones in the pipes. So we're talking about much lower abrasion tendency at that location. So those pedals are usually just hardened with Hardox or some other coating, and that's absolutely sufficient in order to have long-term resistance. Another thing I would like to mention briefly, in the coal pipes, in the long horizontal or vertical sections, in the straight sections, you also see nearly no wear. You only have wear on the bends. So that's usually the only area where you have problems, and of course on the mill outlet where you have a spinning air coming out of the classifier for a few diameters, there's also an abrasion issue there. So erosion, yes, it is an issue, and I think we have all the right means to tackle it for long-term performance of the system.
Thank you very much. The next question is, what is the lifetime of the probes?
Okay, similar question. Our typical lifetime we see is 10, 15 years. It's really long term. I haven't seen a probe now with 20 years because it's simply too long. But 10, 15 years should be easy. And if someone says, I would like to have a guaranteed lifetime of a few years of warranty or whatever, that should be no problem. We have absolutely no problem with that.
Thank you very much. The next question is, what is the maximum concentration or density for these sensors? Are they good for wet environments?
These sensors can measure between, I would say, 50, 60 grams per cubic meter of dust and 5 kilograms, 5,000 grams per. So it's a very, very wide range that we can measure. A few things must be said, however. When you go above 1 kilogram per cubic meter, your flow properties change. In some materials, up to 2.5 kilograms per cubic meter, the transport conditions are still quite well, and they behave like a lean phase conveying system. But then at some point, depending on the material, in biomass it starts early, in coal it starts later. At some density, it just flip-flops to a completely different pattern of flow. Then you can see velocities jumping up and down and surging, pulsating flows. So we can still measure that, but the measurement gets less and less meaningful to control something. So I would say up to several kilograms per cubic meter, we should be fine. Concerning moisture, that question needs to be answered in conjunction with temperature. If you have very moist material, but on the outlet of your classifier, it leaves the classifier so that the moisture has evaporated and it's transported as steam, our measurement will not see the steam, so the moisture will not affect us. If you have pipes that are soaking wet and you really have raw moisture in the pipes, then of course our measurement will see that because microwaves react to moisture. So if there is moisture, we should be measuring above the dew point.
Thank you very much for this answer. And another question is, the accuracy of 5% is stable down to what turn-down ratio?
Oh, that's a difficult one, because it's hard to prove. The first one that is important to see is that our measurement is linear, because it's a time measurement, right? So the typical turn-down ratio issues that you see with a delta P device, we don't have. A delta P device with a turn-down ratio of 4 is very, very good. If it's 5 or 6, it's usually not, I don't usually buy that. The velocity measurement has a turn-down ratio easily of 10. We can measure a few meters per second up to 50, 60, 70 meters per second. So a very, very big turn-down ratio. And the density is the same. So we don't see any nonlinear effect, and we believe that our accuracy will be also working at very high turn-down ratios. I'm afraid I cannot give you clear numbers and say it will stay the same because it's very hard to verify. Yeah? There's no other method that can do this. A dirty pitot cannot measure at this low load. So I would say it will probably, as a relative measurement, deteriorate a little bit, but far less than traditional measurements method that are based on delta P or something else.
Thank you very much, Hans, and thank you everyone for all your questions. As I have mentioned, your questions will also be available to be answered at a later date. I'm afraid that this will be all the time that we'll have for questions in today's session. So that just leaves me to thank Hans-Georg Conrad for this presentation and Promecon Process Measurement Control GmbH for sponsoring this session. To the attendees, you will receive an email telling you how you can access the on-demand version of this webinar, or you can access this through our website, which is www.business-review-webinars.com. We look forward to sharing further webinars with you, so please do keep an eye on the website just mentioned. And you can also follow us on Twitter @BRWebinars or join our LinkedIn group, Business Review Webinars, for daily updates. Thank you all once again, and I hope that you have a lovely day.